300 panicked passengers, one massive wide-body cabin, and exactly 90 seconds to vanish before it is too late. Welcome to the hidden world of emergency evacuation design. Most of us see an aircraft as a means of travel, but to an engineer, it is a complex puzzle where every millimeter is calculated to prevent a catastrophe. Today, we've stripped this plane to its skeletal frame to reveal the invisible engineering that turns total human chaos into a mechanical certainty. Can the human body beat the clock when every second counts? Let's look at the science of survival. In aviation, we talk about the golden hour in medical emergencies, but in a crash or fire, we live in the golden seconds. This is where survival is determined not by luck, but by rigorous engineering. There is a federal mandate, a strict requirement that every person on a plane, no matter the size, must be able to exit in under 2 minutes. Specifically, the industry standard is 90 seconds. To achieve this, engineers have to account for the psychology of panic. When the cabin fills with smoke, human instinct is to freeze or push. To counter this, the entire architecture of the movement is mapped out before the first seat is even installed. The most iconic part of any evacuation is the slide, but these aren't just inflatable mattresses, they're masterpieces of high-speed physics. When a flight attendant pulls that handle, a chemical reaction triggers what are known as aspirators. These devices are incredible. They use a small amount of compressed gas to pull in massive amounts of ambient air, inflating these enormous structures in under 6 seconds. But inflation is only half the battle. Once the slide is out, engineers have to calculate the angle of the slide and the coefficient of friction on the material. If the slide is too steep or too slippery, passengers hit the ground at dangerous speeds. If it's too slow, you get a pile-up at the door, which is a death sentence in a 90-second countdown. The goal is to move bodies at maximum velocity without causing a single bottleneck. Now let's go back inside. Imagine the power has failed and the cabin is filled with thick thermal smoke. In this environment, overhead lights are useless. Smoke rises and obscures them instantly. This is why engineers developed floor-track lighting systems. These systems are designed to remain visible even when you can't see your own hand in front of your face. But it's not just about visibility, it's about neuroscience. Engineers specifically use green wavelengths and unique pulse patterns because green is more easily processed by the human eye in low-light conditions, and those specific pulses are designed to override the human brain's natural tendency to freeze during a crisis. The light doesn't just show you the way, it pulls you toward the exit. The layout of the cabin itself is a calculated choreography. Have you ever wondered why the aisles are a specific width? It's not just for the drink trolley. The cabin width and seat pitch are engineered to ensure that 2 people can pass through an aisle simultaneously without jamming. But the real secret lies in what engineers call the dead zone, usually located at the galley. On a normal flight, this is where they prep your coffee. In an emergency, this area acts as a critical staging area. It is designed to regulate the pressure of the exiting crowd. By giving the human flow a place to momentarily expand before narrowing into the exit door, engineers prevent the arch effect, a physical phenomenon where too many people trying to squeeze through a door at once actually creates a structural block that stops anyone from getting out. How do we know any of this actually works? Before any new aircraft is allowed to fly passengers, it must pass the dark room certification. These are extreme high-stakes tests monitored by the FAA and EASA. They take a full load of real people, put them in a pitch-black cabin, and tell them they have 90 seconds to get out. The catch is that the testers block half the exits at random. As we move into 2026, engineers are using advanced simulation data to predict the panic factor. This data is so precise that it allows them to adjust the door hinge resistance. If a door is too easy to swing open, a panicked passenger might throw it too hard and damage the mechanism. If it's too heavy, it slows the flow. Every newton of force is accounted for to ensure that even in a state of total terror, the exit remains a mechanical certainty. When you step onto a plane, you are entering a space where every shadow, every light, and every inch of the floor has been designed with one goal: getting you out. Engineering doesn't just build the wings that keep us in the air, it builds the systems that ensure we can leave the plane when things go wrong. It turns a potential disaster into a survivable system of movement. Next time you look at the floor track lighting or walk past the galley, remember, you're looking at the invisible architecture of your own survival.